Welcome to Dr. Liu's VCE Science. In this episode, we take a deep dive into the most challenging spectroscopy questions from the 2025 VCE Chemistry, NHT, official exam. By deconstructing question 25, 26, and the high-yield 13-mark question 8, I will demonstrate how to build a logic ladder to deduce the final structure of an organic compound with absolute certainty. This compound features two distinct carbonyl environments, an amide and a ketone. While both functional groups contain a carbonyl, their unique chemical surroundings cause them to absorb infrared radiation at different wave numbers. Referring to item 22 of the data book, we can identify these specific ranges. Ketone, C equals O absorbs between 1680 to 1850 cm to the power of 1. Amide, C equals O absorbs between 1630 to 1680 cm to the power of 1. The trap in this question lies in recognizing that these two carbonyl groups are not equivalent. Their different electronic environments result in two separate, characteristic peaks on the IR spectrum. The position of a carbonyl peak in an IR spectrum depends on the stiffness of the C equals O bond. Higher bond strength leads to a higher wave number, further left. Two main electronic effects are at play: resonance, which weakens the bond, and induction, which can strengthen it. IR carbonyl summary amide, 1630 to 1680 lowest wave number. Nitrogen's lone pair resonance gives the C equals O single bond character, making it the loosest bond. Carboxylic acid, 1680 to 1740 middle low. Hydrogen bonding between molecules, dimers, pulls on the oxygen, slightly weakening the double bond. Aldehyde, 1660 to 1745 baseline. A standard double bond with minimal electronic interference from the attached hydrogen. Ketone, 1680 to 1850 high middle. Strong double bond with slight inductive support from neighboring carbon atoms. Ester, 1720 to 1840 highest wave number. The electronegative oxygen pulls electron density away from the carbonyl carbon, induction, tightening the double bond into a very stiff spring. 1. Spectrum analysis. The 1H NMR spectrum reveals three distinct proton environments based on the N+1 splitting rule. Quartet, approximate 4.4 ppm indicates a proton with three neighbors, N+1 equals 4. Singlet, approx 2.3 ppm indicates protons with zero neighbors, N+1 equals 1. Doublet, approx 1.6 ppm indicates protons with one neighbor, N+1 equals 2. 2. Evaluating the options. Eliminate A. The equivalent methyl groups in CH3, 2CHOH would split the neighboring methyne, CH, proton into a septet, which is absent here. Eliminate B. A carboxylic acid would show a characteristic singlet far downfield at 10 to 12 ppm for the COOH proton. Eliminate C. While the acetyl group CH3CO provides a singlet, the ethyl group, CH2CH, would produce a quartet and a triplet pair, not a doublet. Correct option D. In CH3COCHClCH3, the isolated acetyl methyl, CH3CO provides the singlet. The CH proton, coupled to three methyl protons, creates the quartet, and in turn, that CH proton splits the terminal methyl group into the observed doublet. The rapid decolorization of bromine water, from brown or orange to colorless, indicates that compound Z is unsaturated. This means the molecule contains at least one carbon-to-carbon double bond or triple bond. The type of reaction is an addition reaction. Specifically, it is a halogenation, bromination, where the bromine atoms add across the multiple bond, breaking the pi bond to form a saturated haloalkane. Determining the molecular mass of compound Z. When looking at the mass spectrum, we must distinguish between the molecular ion M+ and the M+1 peak. The nitrogen rule, since the prompt confirms compound Z contains no nitrogen atoms, and we have already identified it as a hydrocarbon, the molecular mass must be an even number. Evaluating the peaks. The peak at MZ equals 84 is even. The smaller peak at MZ equals 85 is odd and represents the M+1 ion, caused by the presence of the naturally occurring C13 isotope. Conclusion: therefore, we identify 84 as the true molecular mass, M+, not 85. Based on the decolorization of bromine water, compound Z is identified as an unsaturated hydrocarbon. Assuming the presence of a single carbon-carbon double bond, we apply the general formula for alkenes, CnH2n. By substituting the relative atomic masses, C equals 12.0, H equals 1.0, into the molecular mass, M equals 84, identified from the mass spectrum, we establish the following equation. As we calculated, this corresponds to the loss of an ethyl group, C2H5, from the parent ion. The species responsible is the fragment ion, C4H7+. Note: the square brackets and positive charge are mandatory for marks. The iodine value is a chemical parameter used to quantify the degree of unsaturation, the number of double or triple bonds in a substance. It is defined as the mass of iodine in grams that is consumed by 100 grams of a chemical substance. 1. Determine the molar ratio. Since compound Z has one carbon-carbon double bond, it reacts with iodine in a 1:1 molar ratio. 2. Calculate the amount, mol, of compound Z. Using the mass, 100 g, and the molar mass we previously identified, M equals 84.0 grams per mole. 3. Determine the amount, mol, of iodine based on the 1:1 ratio. 4. Calculate the mass of iodine. Using the molar mass of diatomic iodine. (1) Comparison of peaks and formula. Molecular formula: C6H12, 6 carbon atoms total. 13C NMR spectrum, 4 peaks, 4 unique carbon environments. 2. Information provided about the arrangement. The discrepancy between having 6 carbons, but only 4 signals indicates that compound Z must have symmetry. Specifically, non-equivalent carbons. There are 4 distinct electronic environments in the molecule. Equivalent carbons, 2 pairs of carbon atoms, must be in identical environments, symmetrically equivalent, to share a single peak, while the remaining 2 carbons are unique. Double bond conformation: the 2 peaks downfield, greater than 100 ppm, confirm the presence of the 2 carbons involved in the carbon-carbon double bond, while the 2 peaks upfield, less than 40 ppm, represent the saturated alkyl carbons. (1) Integration curve analysis, peak at 1.0 ppm. The integration curve, the step-like line above the peak, represents the relative number of protons in that environment. By comparing the heights of the 3 integration steps, the ratios are approximately 2, 4, 6. For a molecule with the formula C6H12, 12 protons total, this means the peak at 1.0 ppm represents 6 protons. Indication: this suggests the presence of 2 equivalent methyl groups, 2 times CH3.2. Chemical shift and splitting analysis. Chemical shift, 1.0 ppm. This value is characteristic of protons in a saturated alkyl environment, specifically a methyl group, RCH3, far from electronegative groups, or double bonds. Splitting pattern, triplet according to the N+1 rule. A triplet indicates these protons have 2 neighbors, N+1 equals 3. Bromine water test, presence of a carbon-carbon double bond, alkene. Mass spec, MZ equals 84, molecular formula is C6H12, Mr is even, no nitrogen. Mass spec, MZ equals 55, loss of an ethyl group, C2H5, to form the stable C4H7 plus cation. 13C NMR, 4 peaks, high degree of symmetry reducing 6 carbons to 4 signals. 1H NMR, singlet at 4.7 ppm, a terminal double bond bonded to a carbon with no protons, equals CH2 attached to a quaternary carbon. In hex 3-ene, the protons on the double bond, HC equals C, would not be a singlet. If we look at the structure of hex 3-ene, the vinylic protons, in red bold, are adjacent to CH2 groups. According to the N+1 rule, those protons should be split into a triplet, or a more complex multiplet, because they have 2 neighboring protons. The fact that the official answer is 2-ethyl but 1-ene perfectly explains the singlet at 4.7 ppm. In 2-ethyl but 1-ene, the 2 protons are on a terminal carbon, CH2. The carbon they are attached to is bonded to a quaternary carbon, a carbon with 4 bonds to other carbons and 0 hydrogens. Since N equals 0, the splitting is 0 plus 1 is equal to 1, a singlet. IR Spectroscopy, question 25. Focuses on identifying carbonyl functional groups using IR spectra. Emphasizes that different carbonyl environments absorb at different wave numbers due to electronic effects. Key idea: amide and ketone carbonyls are not equivalent, so 2 separate peaks must be recognized, explains the exam trap. Assuming all C equals O groups absorb at the same frequency. Carbonyl IR summary. Amide, lowest wave number, strong resonance. Carboxylic acid, slightly higher, hydrogen bonding. Aldehyde, baseline. Ketone, higher, inductive effects. Ester, highest, strong induction from oxygen. To the power of 1H NMR spectroscopy, question 26. Uses splitting patterns, N+1 rule, to identify a compound. Interprets a quartet, singlet, and doublet to deduce proton environments. Demonstrates systematic elimination of incorrect options using expected splitting patterns. Chemical shift positions. Correct compound identified because its structure uniquely matches all observed NMR features. Chemical tests and reaction type, question 8a. Bromine water decolorization confirms the compound is unsaturated. Identifies the reaction as an addition, halogenation, reaction, indicating the presence of AC equals C bond. Mass spectrometry, question 8b. Molecular formula. Uses the nitrogen rule to confirm no nitrogen is present. Identifies the molecular ion peak, M, Z equals 84, and ignores the M+1 peak. Determines the molecular formula as CH, consistent with an alkene, fragmentation. Explains the M, Z equals 55 peak, as loss of an ethyl group, CH. Identifies the fragment ion as a CH, stressing correct exam notation. Iodine value calculation, question 8c, introduces the iodine value as a measure of unsaturation. Uses a 1:1 molar ratio between iodine and C equals C bonds. Calculates the mass of iodine reacting with 100 g of compound, reinforcing stoichiometric reasoning. To the power of 1 cubed C NMR spectroscopy, question 8d, molecular formula has 6 carbons, but spectrum shows 4 peaks. Conclusion: the molecule has symmetry, causing equivalent carbons to share signals. Downfield peaks confirm alkene carbons, upfield peaks indicate saturated carbons. High resolution to the power of 1H NMR, Question 8e uses integration ratios 2, 4, 6 to count protons. The 1.0 ppm triplet represents 6 equivalent protons, indicating 2 equivalent methyl groups. Chemical shift confirms a saturated alkyl environment. Final structural deduction, questions 8f, and conclusion. Combines all evidence, bromine test alkene. Mass spectrum CH fragmentation ethyl. Loss to the power of 1 cubed C NMR symmetry. To the power of 1 H NMR terminal alkene with a quaternary carbon. Final structure identified as 2-ethyl but 1-ene. The singlet at 4.7 ppm is highlighted as the key smoking gun, proving a terminal equals CH group with no neighboring hydrogens. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.